now let's look at an example of a Markov decision process. So this particular example has been borrowed from Sutton and Bartow's reinforcement learning textbook. It's in page 52 of the third chapter of the textbook. It's example 3.3. So the example has been used as is, right? So no changes have been made, and whatever images have been used in the example in the textbook, they have been reproduced here. No screenshots have been taken, so they have been reproduced from scratch. So let's start. So the situation is as follows. So you have a room filled with empty soda cans, right? So you have a lot of empty soda cans that you can see here, and you have a robot. So you have a robot that is going to go and look for these cans. Right? So it's tasked with collecting these empty soda cans. So it could either do that, or it could wait in its location, and the people who are in the room could come and deposit the cans to this robot. Right? So you have this mobile robot that is placed in some kind of an office environment. You could think of this as an office environment where there are quite a few empty soda cans lying around. Okay, so the job of this robot is to go and search for these empty soda cans. Right? So that is one option that it could exercise. Alternatively, what it could do is it could stay where it is and can wait for the people in the room to come and deposit the empty soda cans into the bin associated with this. Right? So assume that this is a mobile dustbin of sorts, right? So there is a dustbin or a bin associated with this robot where these soda cans are collected. Right? So the simple catch here is that either the robot could explore and collect these cans, or it could wait for humans to come and deposit cans into its bin. Okay, so this is the situation. So how does the robot know where the cans are? It has some sensors that are given to it for detecting these cans. Okay, so using the information from the sensors, it will know how far away a can is. Okay, once it knows how far away a can is and in which direction it is, it needs to actually navigate to that spot, right? So for that, it's given certain motors, right? So that will help the robot to navigate and go to that particular position. And once it goes there, it needs to reach out to the empty can. It needs to reach out to the empty can, pick it up, and place it inside the bin that is associated with it. Right? So there are two things involved. One is, in fact, three things. One is sensing these cans, and once you sense these cans, you need to navigate to that spot. So once you are close enough to a can, you need to pick it up and place it inside your bin. So these are, largely speaking, three operations that the robot has to do, right? So there is a separate set of motors for navigation, and there is a separate set of motors for moving its arm close to the can and then gripping it and then placing it inside its bin. Okay, so there are separate systems for these two. So this is how the control of the robot works, right? And as we said before, the room is filled with empty soda cans and also some humans, and there is a recharge station at one corner of the room. So what is the point of having this recharge station? So this is a robot, right? It's a mobile robot that runs on battery. Okay, so every time this robot is going to search for cans, its battery is going to run down. Okay, since the battery is finite, there is a possibility of the battery entirely running down. Okay, if such a thing happens, if the battery entirely runs down all the way to zero, then a human has to intervene, pick the robot, take it to the recharge station, and get it recharged. Okay, this is one scenario. Alternatively, a better scenario for a robot, an autonomous agent, right, is it should be able to sense that its battery level is quite low, and it should be capable of going of its own accord to the recharge station and getting itself recharged. Okay, this is the ideal scenario. This is what we want, right? But the other possibility is also there. So let's quickly summarize the situation that we have here. The robot is a mobile robot that finds itself in a room full of empty soda cans and also some humans in it. Okay, the robot runs on battery. Its task is to go around searching for cans, collecting them. There is also another possibility of responsible humans coming to the robot while it is waiting and depositing empty cans into it. Since the robot runs on battery, its charge will go down when it searches for these cans. When it moves around and moves its arm and gripper, and when it searches for these cans, its battery is going to run down. Okay, so there are two possibilities. Either the robot, being an autonomous agent, should be capable of going to the recharge station and recharging itself. In the event of the robot, running out of charge before going to the recharge station, what will happen? A human has to rescue the robot, take it to the recharge station, and get it recharged. Okay, so this is the summary of the problem that we have here. So how do we formulate this as a Markov decision process? Okay, so before even we go there, let's try to understand what problem we are trying to solve. Okay, in order to understand that, we look at three different cases, three different RL problems, where the agent environment interface is drawn at different levels. First problem that we'll take is navigation. So what is the problem of navigation? Even before that, you have to sense the cans. Okay, assume that you have sensed these cans using the sensor information. Okay, gathering the sensor data, you have sensed where a can is. So the next task once sensing is done is to navigate to that point. In fact, even while you are navigating, you need to continue to keep sensing. Right? So you need to it's not like you sense and then you close your eyes and then you move forward. So this, even while you're navigating, you probably need to keep sensing the environment, seeing how close the can is, and so on and so forth. Right? Assume that that's the problem that you have to solve. Right? Move close enough to soda cans. Okay, you have to move close enough to an empty soda can. How do you achieve this? This is your goal. How do you achieve this? By changing the torque to the motors, or by choosing what torque to apply to your motors. Okay, so that is what helps us determine how fast to move. Right? It's not just the speed of motion, it's also the direction of motion. Right? So you may have to orient yourself in the right direction before moving. Right? So you may have a motor that controls your orientation about your axis. Okay, so there are different kinds of motors, and you have to specify the torques to these motors in order to solve the navigation problem. Okay, what might be the rewards? You get a positive reward if the robot is within some delta distance of a can. Right? So what is our task? Is to move close enough to a soda can. It doesn't do if you are like 5 meters away from the can. Right? So you have to move within at least say 30 centimeters of it, so that your arm can come down and pick the can. Right? So for that, you need to move close enough to the can. So you get a positive reward if you are able to reach within some delta, where delta is a small number, distance of a can. What could be a bad situation for the robot to find itself in? Toppling. Right? So if you apply too large a torque, right, to one of these motors, what could happen is it might topple. Or what could the another negative scenario could be, if the robot goes close to say a wallet. Right? So like some human has dropped a wallet in the room, and for whatever reason its visual sensors identifies the wallet as a can. Right? Maybe it's some kind of error there. Right? So it could end up trying to get close to that wallet instead of an empty soda can. Right? That could also count as a negative reward. Right? So I've not specified all possibilities here. It's just to give you an idea of what could be positive rewards and negative rewards in this situation. So this is a navigation problem. Now let's look at another problem. Right? Assuming that you have managed to navigate, right, and move close enough to an empty soda can, what is the next problem that you have to solve? You need to pick the empty can and place it inside your bin. Okay, that's what you have to do. So what could be the actions here? Again, torques to motors. Right? Only difference is that the motors here will be different. Right? The motors here will not control how the robot moves with respect to the room, but how the arms and how the arm and the gripper moves relative to its own body. Right? So there will be a separate set of motors that govern these actions. Right? So you will be controlling this. So notice how the agent environment boundary or interface is drawn at a different location. Right? So that's what we need to observe. Positive rewards could be the bot successfully picks an empty can and places it inside its bin. Negative reward could be if it fumbles, right? If it's not able to, let's say it's not able to grip it properly, right? Things like this. So that's one negative situation that the bot could encounter. Finally, let's come to a problem that is at a much higher level of abstraction. Okay, so here you have to search for cans. Okay, I'm not going to worry about how to navigate. I'm not going to worry about how to pick and place a can once I'm close enough to it. I am only going to worry about how to search for cans in the first place. Okay, this may seem like a trivial problem, but if you think about it, it's not trivial, because in every situation you can either search actively, in which case your battery is going to run down. Okay, or you could wait. You could wait for humans to come and deposit cans into your bin, or you could go and recharge yourself. Right? So you have to decide, right? You have to make these decisions. And what happens if you keep on searching? If you keep on searching, the battery will run down all the way to zero, and a human will have to come and rescue you, right? And that's not a good thing for an autonomous agent like a robot, right? So that's not what you want. On the other hand, let's say you simply sit and wait, okay, and you have a room full of humans who, are, let's say, some of them are not, or most of them are not responsible enough to come and deposit a can into your bin, right? Or they feel that you are anyway a robot. It's your job to go and collect the empty cans. I am not, me as a human, I have delegated this task to you, so you should do the job of searching for cans, right? So waiting may be a bad thing to do, right? Or it may not be always optimal, right? So you'll also have to think about when to recharge, right? If I'm having a very high level of charge, okay, it may not be the right thing to recharge. On the other hand, if I'm dangerously low, if I have dangerously low charge levels, then it might be a good thing to recharge, right? So this is a non-trivial problem to solve. What could be the rewards? You get a positive reward if the robot collects a can, okay, this makes sense. And negative reward if the robot's charge goes all the way down to zero, because you'll have to be rescued by a human, and you don't want that. Okay, so these are three problems, and you can immediately see that each one can be formulated as a reinforcement learning problem, and the agent environment interface is at different levels for each of these problems. So what we'll do now is we'll focus on the search problem. Okay, it's simple enough to try to understand this and see how we can extract an MDP, or how we can formulate an MDP surrounding this situation. Okay, so there could be now two charge levels, right? So the charge level in the battery could either be high or low. So this is a simplifying assumption, right? So if you think about it, we could specify the battery level at a much more finer level of granularity by using, say, some numerical values like 0 to 5, right? On a scale of 0 to 5, what is my battery level? It could be 0, that's battery is totally down, or it could be 5, full charge, right? So we could have that kind of a setup for the battery level, in which case you'll have 5 different states, right, that your charge level or battery level could take. We could do it that way, but what we are doing here is something very simple. So the battery level is going to be binary. It could either be high or low. Okay. Now, if the battery level is high, the agent, in this case the robot, can take two actions, right? It could either search actively for cans, in which case the battery level is going to keep going down, or it could wait in its place and expect humans to come and deposit empty cans into its bin. Alright? There's no point in trying to go and recharge itself at the recharge station or the charging station. Why is that? Because when you're waiting, your battery level doesn't change. It doesn't go down. Okay, so if you're at state high, if your battery level is high and you decide to wait, nothing is going to happen as far as your charge level is concerned, so it doesn't make sense to go and recharge yourself. On the other hand, when your battery level is low, you could still be ambitious and search for cans. Okay, there's a very high chance that you'll end up depleting your battery level all the way to 0. Okay, or you could be a little more sensible and wait, okay, and expect humans to come and deposit cans into your bin, or you could do the safe thing by going and recharging yourself, right? So only difference between the actions that are possible in these two states of high and low is that the low state has one extra action of recharging, right, which is not there in the state high. There are two outcomes. Desirable outcome is collecting can, right? Whenever you collect a can, okay, by collecting it could happen either way, right? Either the robot could search and collect, or someone could come and deposit, right? We call both of them collecting a can, right? The outcome is a can is coming into your bin. That's what matters. So that's a desirable outcome. The undesirable outcome is if the battery of the robot runs all the way down to 0. Okay, as we have been saying, for an autonomous agent, that is a bad thing, right? So if a human will have to come and rescue it, right? So a human will have to come and rescue the robot and recharge it, and that's not a good sign. Okay, so that's an undesirable outcome, and we know what a desirable outcome is, right? So what we have done here is we have not really used the terms state, action, reward, right? We have used things like charge levels, okay, and what are the options available for the robot, right? Of course, we have been mentioning state, action, reward here and there, but let's now make it more formal and turn this into a Markov decision process. Okay, so these are your states. The state could be high or low. The actions from each state, as we have just described, could be search and wait for high state and search, wait, and recharge for the low state. So this is what we have. Now, the point to note is that the state here is Markov. Right? So the only information that I need to know to act is whether my battery level is high or low. Right? So I don't need any history of what my battery level was 10 steps before. I don't need to know that, right? I just need to know what my current battery level is to take an action, right? So I don't need to know what my battery level was, for all the time steps in the past, right? I just need to know my current battery level to, know what action to take in the future, rather what action to take now and where I'll go next, right? That depends only on my current battery level, and therefore the state is Markov. Now let's move on. Once you know what your states are, once you have defined what your actions are, the next thing that is needed is a transition probabilities, right? We need the transition probabilities in the rewards, or even before that, we need to know what the transitions are, right? If you are in a particular state and you take an action, where all can I go? How probable is it that I will go to a particular state, and how probable is it that I will get some reward associated with the transition? Okay, so now let's look at it one by one, right? One action at a time. So what we have here is, so what we'll be filling up now is what is called a transition graph, right? So it's a graph that you have studied, the graph data structure that you have studied in the PDSA course, right? So what are your nodes going to be? The nodes are going to be of two types. It could be either a state node or it could be an action node, right? Every node could be either a state node or an action node. So a state node is denoted by this open circle here, and an action node is denoted by a solid circle here, right? So these are two types of nodes. Let's now take up the state high and see what actions are possible there, wait or search. So if you take the first action, let's take wait to be the action here. If you decide to wait given the state high, what is going to be the next state and what's going to be the reward? Okay, so if you decide to wait, your battery level is not going to change. It's certainly not going to go down, right? Or go up anyway, so it can't go up. So the battery level is not going to change. Okay, so you will remain in state high. Okay, and this will happen with probability 1. Why is that? It's a deterministic transition, right? So there's no way you are going to go to the state low. So it's a deterministic transition. So the probability associated with that is going to be 1. And what is the reward that you will get? So here what we'll do is we'll not state the exact reward. Instead we'll state the expected, we'll add the expected reward if you start from state high, decide to wait and transition to high. So it's if you recall what we did in the lectures, it is the value R of S prime. It's the expected immediate reward starting from state S, taking action A and transitioning to S prime. Okay, so we are denoting this by R weight. Okay, R subscript weight. So 1 that you see there is the probability of transition. R weight is the expected immediate reward starting from state high and deciding to wait and transitioning to high. Okay, so you might be wondering, why is this R underscore weight? Okay, why is this only a function of the action? In this particular case, if you think about it, the number of cans that you collect, right? So R weight is what? It's the expected reward. So you can think about reward of 1 associated with every can that is dumped into your bin. So a reward of +1 for every can that is dumped into the bin. So the expected reward for this particular situation is what? The average expectation is nothing but an average, right? So the average number of bins that you are likely to collect when you are in state high and you decide to wait. Okay, so if you think about it a bit, when you are collecting these cans, your battery level really doesn't matter, right? So what matters is, are you waiting or are you searching? Okay, so that's the only thing which is going to influence how many cans you receive, right? If you're going to search, the dynamics are going to be different, right? So you might there is a possibility of finding more cans because you're actively searching for them. On the other hand, if you decide to wait, then you have to be at the mercy of humans who are responsible enough to come and deposit cans into your bin, right? So you see that the expected immediate reward in this case depends only on the action. However, this is for this particular MDP, right? In general, the expected reward depends on S, A and S prime, right? So this is only for this particular scenario. So that's what happens if you are in state high and you decide to wait and you transition to state high again. What is the other action which is possible from state high? Search. Okay, so if you decide to search, this is slightly more involved and also more interesting than the situation where you wait. So think about where you'll end up. If you decide to search, either you may be lucky that in the sense that you may end up with a very high battery level, or not a very high battery level, but still high enough to qualify as high enough so that your battery level qualifies as high or goes into the bucket high, or you could end up with the state low, right? Your battery could run down and cross the threshold between high and low, so you might end up with state low. Okay, let me repeat this. When you are in state high and you decide to search, one of two things could happen. One, you could remain at the same battery level. Remember that we are abstracting out a lot of things, so the exact battery level is not known. We only know whether it is high or low, right? So when you search, the battery level is going to run down, but it may not cross the threshold where it becomes low, right? If you think about the battery level as some quantity that is on an interval between 0 and 1, right? 1 meaning high, 0 meaning low. Now the high level could be 0.5 to 1 and the low battery level could be 0 to 0.5. So if you start with a battery level of 1 and you start searching, maybe you end up with 0.6, right? So 0.6 is greater than 0.5, so we'll still call that high. Okay, so what we have done is actually we have abstracted the exact battery level, okay, or exact charge level, right? So you must remember that, or you must realize that there is still a possibility that when you start from high and you search, you can in fact end up in the state high with some probability alpha, right? With a probability of 1 minus alpha, you could end up in state low. Okay, and when you are searching, you will collect a certain number of cans. The average number of cans you will collect, the expected number of cans that you will collect is R search. Okay, now we have exhausted all possible actions from the state high. So now we come to state low. What actions are possible? 3 actions are possible here. Let's again begin with wait. If we decide to wait, charge level is going to remain the same. We are going to go back to state low. with unit probability. Okay, if we decide to search, again one of two things could happen. You could remain in the same level low with some probability beta, but on the other hand, what might happen is you might totally run down, your battery level might totally run down, you might completely run out of charge, in which case, unfortunate, you have to wait for a human to rescue you, right? You'll have to be rescued by a human. He has to take you to the battery station and recharge you, right? That is an undesirable scenario. Therefore, we penalize the agent by giving it a reward of -3. A reward of -3, that's a penalty, right? So that's what happens. Okay, so this is the scenario. Now, one final action is possible from the state low, which is that of recharging. If you decide to recharge, you will deterministically move to the state high, right? So, and the reward along the way will be 0, right? It's not, you don't collect any cans, right? Assume that you don't collect any cans while you are recharging. Okay, one final point about this transition graph before we move forward. Notice that you have the same action node here. In some sense, it looks same, right? You have wait here, you have wait here, you have search here, you have search here. Now, are they the same or are they different? Okay, so if you think about it, these two action nodes, even though they correspond to the action weight, they are not just talking about the action weight in isolation. They are actually talking about state action pair, right? So this weight, you don't perform actions in isolations, right? In isolation. So you always perform an action from a given state. Okay, so these even though they are called action nodes, a more appropriate way to understand them is they correspond to state action pairs. Okay, so this weight here, what does it mean? It means starting from high, I decide to wait. So it actually corresponds to high comma wait. Okay, so it's important to keep this distinction in mind between the state nodes and the action nodes and how they are related to each other. Okay, so far we have been looking at the transition graph. Let's now try to understand the tabular form of the Markov decision process. So what do we have here? We have SA transitioning to S prime. There's a transition probability P of S prime given as comma A, and the expected reward starting from state S, taking action A and transitioning to S prime. So it's very simple to fill this up once you have understood the transition graph. So S is high. Let's start with S being high and you deciding to search. Okay, you could end up in either high or low with a probability of alpha and 1 minus alpha respectively, and the expected reward, immediate reward, is going to be R search, right? R search could be, say, something like 7. So on an average, you are going to get 7 cans. You're going to collect 7 cans while you are searching from the state high, right? As we have just mentioned before, the state doesn't matter. Okay, you will collect on an average 7 cans while you search, right? That's what it means. If you decide to wait, on an average, you may collect, say, 3 cans. So our weight will be 3. Okay, so that could be one scenario. But the transitions are deterministic because when you wait, charge level doesn't change. Okay, so now you can think about something similar for the state low. Okay, you search, you wait, and you recharge, right? So you can just fill up the rest of the table. So with this, we see that we have complete description of a finite Markov decision process. So why is it finite? States are finite, actions are finite, and rewards are bounded, and also they are finite here, right? So this is a finite MDP. So that gives a description of the Markov decision process. What we have next is to understand how a policy will look like for this problem. Let's look at a deterministic policy to begin with. Right, for a deterministic policy, for each state, you know exactly which action to take, and always that action will be taken by the agent. Correct? So in this case, if the state is high, the agent decides to search. Okay, seems like a reasonable thing to do. If the state is low, the agent recharges, right? Always this is what happens. Okay, every time the agent is in state S equal to high, it searches. Every time it's in state low, it recharges. Okay, this is a deterministic policy. So what about a stochastic policy? It would look something like this. So every time the agent is in state high, it could either take the action search or it could wait. Okay, 80% of the time it decides to search, 20% of the time it decides to wait. Okay, on the other hand, when the battery level is low, the state is low, it decides to wait 60% of the time, search 10% of the time, and 30% of the time what it does is it decides to go and recharge itself. Okay, so these are two kinds of policies. So for the deterministic policy that we have, let's sample a trajectory and see how it looks. Okay, and we'll also compute the return corresponding to it. So the trajectory starts from S0. You take action A0 and you transition to S1 with the reward of R1. Recall that the next state and reward are jointly distributed given the current state and action, right? So, and then you keep going on and on. So you can think of this as a continuing task with some gamma, right? So let's say we start with state high, and since we are following the deterministic policy, we have to search, right? So we have to search. If you decide to search from the state high, there is some probability with which you could go to state high, some probability with which you could go to state low. So assume that for this particular sample, the state ended up being high with some reward of 2, right? So this would be like 2 cans being collected, right? So notice that this 2 here is not the expected immediate reward. It's actually the number of cans that you collect, right? So this 2 should not be equated to R search. Okay, it's actually a sample from this particular MDP, right? So you have sampled a reward from this reward distribution, right? It's not the expectation. So here it concretely means 2 cans have been collected while searching. Okay, so this, you are now in state high. Okay, now you decide to take the action search again. You continue to search because that's what the policy says. Now it's more likely that you end up in state low. Okay, and let's say you manage to collect only 1 can in this process. Now you're in state low. What do you decide to do? You decide to recharge. That's what the policy says. And if you recharge, you deterministically transition to state high, and you don't get any reward in this process. You can keep going on and on, right? So what will be the return corresponding to this trajectory? G0 is going to be 2. That's the first reward. R1. So GT is RT plus 1, right? So G0 is R0 plus 1 or R1 plus gamma times R2 plus gamma square times R3, so on and so forth. So discounting factor gamma is equal to, say, 0.9. You could set it as 0.9 and compute this return. Okay. Finally, what we need is value function, right? So what we need to compute is the value function. Value function is what? It's the expected return starting from state S and following policy pi, right? In this case, you have 2 states. So your value function, if you treat it as a vector, you'll have 2 entries, one corresponding to low, that's v pi of low, one corresponding to state high, which is v pi of high, right? In subsequent lectures, we'll learn how to evaluate the value function for a given policy, and after that we'll try to figure out how we can learn an optimal policy, okay, so as to solve the reinforcement learning problem, right? So this is what we'll get in the upcoming weeks. That is the end of this tutorial. Thank you.